Good afternoon and welcome to the Thelma Hansen virtual series on climate change and its impacts on Southern California. As Sherry mentioned, my name is Annemiek Schilder and I'm the director of the University of California Cooperative Extension Office in Ventura County and the Hansen Agricultural Research and Extension Center in Santa Paula. We would like to acknowledge that the Hansen Center is located on land stewarded by the Chumash people prior to occupation. This land was and continues to be of great importance to them, and we are honored to collaborate with and learn from our Chumash partners about protecting our land and water resources in a changing climate. This webinar series is sponsored by the Thelma Hansen Fund. To give you a little background, Thelma was a farmer in Satakoy who a century ago studied mathematics at UC Berkeley. And after she was done, she returned to farming. Upon her passing, she left a generous endowment to the University of California. The Thelma Hansen Fund was created in 1993 to support and maintain university research and extension activities for the sustainability and benefit of agriculture and natural resources in Ventura County. So we chose the topic of climate change due to its urgency and impacts on agriculture and the natural environment that we are already experiencing. We believe Thelma would have been greatly concerned about this issue. And we also wanted to bring science to the public in an understandable format. The scientific underpinnings of climate change may not be clear to most people, even to scientists like myself. And also it may not be clear what you as an individual can do about it or how to prepare for it. Unfortunately, the issue of climate change has become heavily politicized in the United States, which has the most climate change deniers in the Western world, while also being the largest producer of greenhouse gases on a per capita basis. However, scientists overwhelmingly agree that people are causing climate change through greenhouse gas emissions. And think about it. Carbon from fossil fuel reserves that have formed over hundreds of millions of years is being released into the atmosphere over a span of about a century, probably mostly the last 60 years. How could that not set the balance of nature? And even if you're uncertain about climate change or the cause of it, you should consider the risk of doing nothing to mitigate or prepare for it. The economic impact of temperature extremes, fires and floods has already been enormous and is only going to increase. And add to that the potential disruptions by worldwide migrations of climate refugees. But there are things that can be done. Countries around the world are already well on their way in reducing carbon emissions. In my country, the Netherlands, most new houses will not have any gas, will just use heat from the earth and solar panels. And in the US, President Biden just announced plans to reduce US greenhouse gas emissions by 50%. That is from the 2005 level over the next decade. So I hope you will listen intently to our speakers over the next 3 days. There will be some time for questions after each presentation. But for those of you who can stay longer, we will have additional time for questions after the presentations until 6 p.m. if needed. But first, we will have a word of welcome by California State Assembly member Steve Bennett, who represents the 37th district, which includes parts of Ventura and Santa Barbara counties. He was also a Ventura County supervisor for 20 years. And after that, Dr. Sabrina Drill, who is our natural resources advisor, will moderate today's session. Thank you and enjoy.
Hello, my name's Steve Bennett. I'm the 37th District Assembly member representing much of Ventura County and Santa Barbara County in the California State Legislature. I'd like to welcome you to the University of California's Agricultural and Natural Resources special 3-day series, Climate Change, What Does It Mean for Southern California? You know, they've created a really appealing agenda, something I'm really intrigued by. They've got stellar leaders focusing on important discussions about climate change, and in particular, the impacts on agriculture in Southern California. You know, agriculture, as we all know, is hugely important in Ventura County. with Ventura County 2.2 billion in gross value, number 11 in the country in terms of counties with agricultural value. So it's very timely that we have this conversation. You know, I think there's really two ways that climate change is having a big impact on agriculture. One is as a result of the dryness and the higher temperatures and the increasing intensity of storms, we are getting more severe wildfires. And all you have to do is look at the last 5 years to see. We used to not have structures get burned hardly at all in Ventura County, and that certainly hasn't been the case in the last 5 years. And then the other is the effects of droughts becoming longer, more sustained droughts with higher temperatures. And then, like we said before, those dry winds that can blow hard. So as a result, we're going to have a more challenging water equation for everybody. And certainly we've had, when we get some of this surface rain, we're not getting it in quantities to recharge our aquifers in particular. And so those are two important issues that I hope we'll learn some things about with this 3-day conference as we go forward. And let me just talk a little bit about the wildfires. You know, 10,000 acres of irrigated cropland affected when we had the Thomas fire, 60,000 acres of pasture land. Overall economic loss of between $70 and $100 million in agriculture and farm dwellings, etc. And we had lots of people come together to try to help. Certainly the extension, the UC extension was very helpful during that time period. But it is going to be a growing problem for all of us. And wildfires cause two huge problems for us locally, bad air quality, both for the human beings breathing the air, but it also damages crops as you have that really bad air quality also. And then certainly it releases an enormous amount of carbon into the atmosphere. And we're at an unsustainable level of carbon emissions at this point in time. And then when it comes to the issue of water, you know, you see that Ventura County and Santa Barbara County are going to struggle again now that they've officially declared a second year of drought for us. And you have to think droughts coming this frequently with very little time in between, there is a climate impact by this. So I'd like to point out that I'd be happy to talk to any of you about any of the climate change legislation in front of the legislature. I am really proud to be a co-author with David Chu and a bill that I think is really going to be important, AB 545. And what that bill does is push for a plan for offshore wind energy development and to come up with a big plan that could make sure, because we need, with sustainable energy, you have the problem that the sun goes down each night, you have the problem that the wind doesn't always blow, you need both of those in tandem, and then you need good storage of that clean energy when it comes in before we're ever going to go to 100% renewable energy. So that's a bill that's going to mandate the development of a plan for a significant increase in wind energy delivered from floating wind plants out far off the coast, but along the central coast of California. And with that, I hope you guys have a good 3 days. I know I'm going to enjoy as much of these 3 days as I possibly can. And I want to thank, again, the UC for putting this together. Thank you very much.
Well, thanks to Assemblymember Bennett for those important remarks. I'm Sabrina Drill, as Annemiek mentioned, and I certainly look forward to seeing some wind infrastructure replace those oil platforms off our coast there. It's my pleasure to introduce our first speaker, Dr. Daniel Swain. Dr. Swain currently holds concurrent appointments at UCLA's Institute of the Environment and Sustainability, the Capacity Center for Climate and Weather Extremes at the National Center for Atmospheric Research, and is the California Climate Fellow at the Nature Conservancy. He's also the author of the preeminent blog on California climate and weather, Weather West. Daniel.
Well, thanks for that introduction, Sabrina. And thanks again to the organizers for the invitation to give this talk today. So let me just pull up my slides and then I'll get started. All right. So as Sabrina alluded to, what I'm going to be talking about today is climate change in California, not just Southern California, but the whole state, in fact, and how sort of my work on extreme events fits into the bigger picture of what climate scientists have been doing and figuring out over the past few years, and sort of the new findings that have emerged, I think, that change the picture a little bit from what a lot of folks might be assuming about the future of California climate. So without further ado, I will just get started here with a brief primer on California's climate, not climate change per se, but why we have the climate that we do to begin with. And one of the really important aspects of California's climate is that we have a really strongly seasonal cycle of precipitation. So dry summers, wet winters, with some level of transition season in the shoulder seasons in between, in the autumn and spring. Not much of that this year, but at least in a more typical year, that is what we would see. And it turns out that that temporal sequence is actually pretty unusual from a global climate perspective, certainly unusual within the United States. In fact, arguably unique among places within the United States to have that particular seasonality combined with a very high degree of variability from year to year. So it's not just that we have this strong seasonality of precipitation in California, but it's also the case that we have these pretty wide swings from year to year in terms of how much water falls from the sky, from extremely dry years on one side of the coin to really wet ones on the other. And the reason why that is, why we have this sort of intrinsic high seasonality and interannual variability in precipitation, is because we exist at the margin, essentially, the climatological margin, the boundary, if you will, separating the more active mid-latitude or the moister mid-latitude climate from the much more stable and dry subtropical climate to the south. That boundary in winter is often dictated by the position of the Pacific jet stream, that river of high velocity air in the upper atmosphere that defines the storm track. And because that jet stream wobbles around, it varies a lot, not just from day to day or season to season, but also from year to year, it's those variations in the position of the jet stream and whether or not California in a given moment in time is experiencing more of a subtropically influenced climate and a dry one, or a mid-latitude influenced climate and a wet one. So in winter, we have essentially a more mid-latitude climate, and in summer, we have a more subtropical climate. In the dry years, we tend to have a predominant subtropical climate the whole year round. In the wet years, the reverse is true. So as it turns out, this actually is a pretty fundamental aspect of California's climatology, geography, and subsequently its ecology as well, because it requires the plants here and the species here specifically to be at least somewhat resilient to these long summer droughts and these relatively frequent dry years separating the wet ones. And as you might surmise, and I think as is probably intuitive to most people on this on this call, one of the challenges of having such a strongly seasonal cycle of precipitation with so much year-to-year variability is it leaves us quite susceptible to droughts, because there's really only a narrow window in any given year when California is likely to receive the vast majority of its precipitation. It's really just 3 or 4 calendar months during winter, with a little bit extra at the margins, perhaps. But in general, if we miss out on the precipitation during just those few months, that's pretty much it for the rest of the year. So it's relatively easy to get into a drought here because of the seasonality. So it's probably not much of a surprise to folks listening today that California is already a different place than it once was from a climate perspective. California is already a much warmer state than it was certainly a century ago, but increasingly, even relative to 20 or 30 years ago. It's noticeable even on that kind of timescale now. Mountain snowpack is detectably decreasing, and the snow lines are I would say creeping up the mountain slopes, but they're actually, they're running up those slopes in a lot of these years we've seen recently. And along with this, we've seen what is inarguably a large increase in wildfire severity and wildfire impacts. And I'll get into all of these things with a little bit more depth later in the presentation. But I just want to jump right into one of the key findings that helps explain a lot of these changes that we've been seeing and really sort of summarizes all of the sort of characteristics of the climate we expect to emerge as the planet continues to warm in the future. And that is this notion that California may not actually see a distinctly wetter or drier future. We actually may see both a wetter and drier future, depending on exactly where you're talking about and which year you're looking at. And the way this works essentially is that there's this pretty strong expectation at this point from climate models projections that the variability of California's precipitation will increase in a warming climate. So in other words, that we will see, yes, more individual very dry years, but also more very wet individual deluges. So on a bunch of different time scales, more variability between extreme wet and extreme dry from year to year, even season to season as well. And all of this leads to what we have termed an increase in precipitation whiplash, really statewide. Now, this is a projection for the future, but I think as has become increasingly apparent over the past decade, this is also increasingly the lived reality in California. In the last few years, we've had some of the driest years, and in fact, some cases locally, the singularly driest years on record over the past 5 or 6 years, both during the previous drought and in parts of Northern California during the current drought that is ongoing as we speak. But also in Northern California, the wettest year on record, or one of the wettest years on record, just a few years ago in 2016, 2017. And in a lot of ways, that is representative of the kind of future where we expect to see in California, where there is surprisingly little evidence, either in real world observations or in climate model predictions, for a large increase or a large decrease in the overall amount of precipitation that falls from the sky in this part of the world, even in very pessimistic high warming scenarios. But interestingly, those same models, that same data suggests that this large increase in whiplash will emerge. So we will see more droughts, but we're also potentially going to see more floods as well. So that's going to be the sort of the context for the rest of this presentation. And just to look at this in another way, I like maps, but time series are also a mainstay in climate science. This is just a projection for a data point, for a latitude, longitude point relatively close to Los Angeles, just what this might look like in the future, which is to say, no large change in mean seasonal precipitation in California, even in very high warming scenarios necessarily, but a very large increase in the frequency of both wet and dry extremes on either end of it. And so this is just one way of looking at this. And at least the evidence we've seen so far suggests that we should be starting to see these effects right around now. It took a little while to emerge from the noise, but that signal, especially in Southern California, should be emerging in the early 2020s, which we are now in. And arguably, we are now seeing conditions that are consistent with this right now. But one thing I do want to point out, and this is true even to a greater extent in Northern California than it is in Southern California, much of this increase in projected precipitation whiplash is actually expected to occur from increases on the wet side of the precipitation distribution. So while we do expect to see more individual very dry years, we actually expect to see a disproportionately large increase in the extremely wet years on the other end of the spectrum. And I think that's often contrary to a lot of people's expectations about what the future holds. But hopefully I can reconcile that a little bit with expectations in the next few slides. I think it's worth pointing out the global context of this sort of increase in precipitation whiplash in California that we're talking about. This isn't a global phenomena. This is not actually going to occur everywhere. It's not necessarily a hallmark of climate change per se, in a general sense. But what's interesting is that increases in extreme precipitation, so very heavy precipitation events, is a hallmark of global warming essentially everywhere. And this is really critical even in places that are expected to get drier on average, or expected to see little or no change in average precipitation, almost every place on Earth is expected to see a relatively large increase in the most extreme precipitation events. So this may mean, in some regions on Earth, that precipitation actually decreases quite a bit, but that when it does rain, it rains a whole lot very quickly. And this is just some interesting facts from a global climate perspective, is that with each degree centigrade of warming, the global mean precipitation is expected to increase by about 2%. So not a tremendous amount. In some places, it's much more than 2%. In other places like California, it's actually expected to be less than 2% of an increase. But what's really interesting is that, again, the same models, the same physical expectations, extreme precipitation is expected to increase by something more like 5 to 10% per degree centigrade. So 2 or 3 times at least that of mean precipitation. And if you look at the frequency of extreme precipitation, so if you just choose a fixed threshold and ask how often do we exceed it, you actually see increases that are vastly greater than 10% per degree centigrade of warming. So all of this really is to say that mean precipitation patterns globally are actually pretty heterogeneous from a geographic perspective in a warming climate. Some places will get drier, some places will get wetter. But essentially everybody is going to see more extreme precipitation events. And this is consistent with what climate models and what observational reality is telling us about California. And so while this may be obvious, I think it is worth emphasizing. Why do we care about increasing precipitation whiplash in California? And I have 2 examples, one from Southern California and one from Northern California. I think the first one is from Southern California, thinking back to what happened in Santa Barbara and Ventura counties in December and January of 2017, 2018. December 2017 was extremely dry. That was a very dry autumn. There were terrible fires in Northern California earlier that autumn. But then in December, which is, again, very late in the season, a fire started under strong Santa Ana wind conditions and became what was then the largest fire in California's modern history, has since been eclipsed twice in the several years since then. But it was a very destructive and intense fire that occurred at a pretty unusual time of year. It was immediately followed by really devastating and destructive debris flows in Montecito in Santa Barbara County that actually killed a lot of people and destroyed quite a few homes. I was in Santa Barbara County shortly thereafter, and it was pretty shocking to see boulders the size of trucks just strewn about. There was clearly a massive amount of energy, a massive amount of water involved. But what's really striking about all of this, I think, is that if you take the climatological average of weather conditions over that 4 or 5 week period, it was on average mostly sunny and breezy with below average precipitation, which I think almost anybody in those counties would agree did not characterize the sequence of events very well that actually unfolded. And so all of this is to say, if we only consider the changes in average climate, then a lot of times we're really going to miss the point when it becomes really important to understand the changes in extremes. And then in Northern California, I think we have our own example. This just going back a couple more years to the last drought, when all of the reservoirs were at very low levels, Lake Oroville on the left, an example. It looks like that again today, incidentally. But then in February 2017, there was the Oroville Dam Crisis, where there was a near catastrophe in the Feather River watershed. So, weather and climate didn't cause this crisis, but essentially what happened was a series of particularly extreme atmospheric river storm events, which brought a massive amount of water and very warm temperatures, turned what would have been a fairly mundane engineering issue on the spillway of the main dam structure into a genuine crisis, which was that then the extreme runoff from these events caused massive erosion on that spillway and then caused the somewhat euphemistically described emergency spillway, which was really just a glorified dirt hill on the side of the dam, to be put into use. And there was rapid headward erosion on that structure, which resulted in the emergency evacuation of almost 250,000 people. What I think is really interesting about this, aside from being an example of this whiplash once again, is that historical warming in this part of the state increased inflows into Oroville Reservoir during that event by about 30%. And I have it on pretty good authority from folks who were there at the time, the engineers and emergency managers, that a 30% decrease in inflow into that dam probably would have avoided that overtopping of the emergency spillway and actually wouldn't have necessitated the emergency evacuation of hundreds of thousands of people. That 30% increase is due to historical warming of California's atmosphere during the winter. Essentially, more of that water fell as rain rather than snow. So arguably, the outcome here was dramatically altered just by something that we often think is the most mundane aspect of climate change, which is the warming itself. But you might actually consider what would have happened had this event happened 20 or 30 years from now, instead of a few years ago, with an additional 30% increase in the inflow into the dam, into that reservoir during this event. It might have gone from a near catastrophe to something worse. Food for thought. But I think the other aspect of the changing precipitation characteristics in California, despite this relatively modest or minimal change in mean precipitation, is the change in seasonality. And I think this is something that's really starting to become conspicuous. In the last few years, we've really seen this in spades. And unfortunately, 2020, 2021 is probably the best example of this so far, with an extraordinarily dry autumn in 2020, which facilitated a lot of the terrible fires that lasted late into the season. And then also an extremely dry spring. I mean, it's been almost bone dry in a lot of the state this spring, following what was also a pretty dry winter this year. So this year, it's just been dry all around. But interestingly, in recent years, even in years where the winters have been wet, the autumn and occasionally the spring have also been increasingly dry. And this is actually quite consistent with what climate models are telling us should happen in a warming climate. There's a strong expectation that the shoulder seasons will become drier. Not the winter, interestingly, really anywhere in California. In fact, there's some evidence that the core winter months could, on average, become wetter in a warming climate, mostly skewed by the fact that there's going to be some extremely wet individual winters. But what's pretty clear is that autumn and spring are likely to become significantly drier in a warming climate. And I think it's pretty obvious why this has major implications in California. From a wildfire perspective in autumn, and I'll talk more about that specifically later, but also from a snowpack accumulation perspective, snowpack right now in California is down to almost essentially just 25% of average for the date. And while it has been somewhat warmer than average up there, that's mainly because there just hasn't been any additional real meaningful accumulation for the past couple of months. So the late season water just hasn't been falling from the sky. So that leads to follow-on ecosystem stresses and stresses to agriculture as well, because not only have you reduced the amount of water that's going to be available either for active irrigation from urban water supplies or from just on the natural landscape in terms of soil moisture. In addition to that, you've increased the length of the active growing season in a lot of cases. So not only is there less water available, but there's also more water that's being demanded by the atmosphere and also by living plants as well. And I think because I know that there are folks in this conference, both from Northern and Southern California, I really just wanted to drive this point home, which is that a lot of the changes that I'm talking about here today are relevant just about everywhere in the state. So the increase in whiplash, the warming temperatures, the declining snowpack, the increase in wildfire risk, those are all relevant essentially statewide. But there are some latitudinal differences in how we expect things to evolve in the coming decades in a warming climate, and arguably in how things have already started to evolve. And that is to say that really there isn't a lot of evidence for large changes in mean precipitation, as I mentioned, anywhere in California over the course of even a very aggressive warming scenario, though there is some evidence of a slight increase in wintertime precipitation, mainly in Northern California. But in general, there's not, and I just want to emphasize this one more time, there's really not a strong signal for increases or decreases in mean precipitation on average. Although if you had to press me on it, I would guess that Northern California stands a slightly better than 50-50 chance of seeing slightly wetter conditions in a much warmer future, at least from a precipitation perspective, and Southern California stands a greater than 50-50 chance of seeing drier than average conditions, or drier than the 20th century average conditions. But that's not a very high confidence statement compared to the statement about increasing whiplash just about everywhere. And regarding that, what's interesting is that in addition to the year-to-year variability, and in addition to the increasing seasonality of precipitation, We also find an increase in the variability even just within winters. So regardless of whatever else is happening, the variability from week to week within the winter season is expected to increase. So more dry days, more of the time, but much wetter wet events when they do occur more sporadically, which I know is probably not what a lot of folks wanted to hear. So even in places where we might actually see an increase in mean winter precipitation in Northern California, we actually expect there to be drier conditions most of the time. It's just that those individual really wet events are skewing the average by so much that it's overriding the fact that 80 or 90% of the time it's drier. That extra 10% of the time is essentially completely making up the difference. Now, of course, in practical terms, it doesn't really make up the difference from an ecological or water supply perspective or an agricultural perspective. But mathematically, that's sort of what's going on here. And I think that all of this leads to what I think correctly has been described as a bit of a paradox, this notion that there's a simultaneous increase in both water scarcity and overabundance, in some cases in the same place at different times. And this is coming from, just to sum it all up, less precipitation in the shoulder seasons in autumn and spring, but also more, potentially slightly more precipitation in the peak rainy season months for that overabundance issue. More precipitation, but on fewer days. So more intense, but potentially fewer individual storm systems. So this idea that it's increasingly coming in short, sharp bursts, rather than in the kind of more gradual rains that are arguably most beneficial from a water supply and an ecological perspective. Less snowpack as well. I think that's probably more obvious and is moving essentially just in one direction. Although it is interesting that there's been a lot of variability in recent years. There have been some very heavy snow years recently in the Sierra Nevada, as well as some abysmally low snow years. And so while the average is decreasing, the variability appears to be increasing there too. So we still are getting big snow years. It's just that the typical years are seeing significant declines. When it's not falling very heavily. Again, sort of an amplification of that historical pattern. So all this put together really points to not only an increasing risk of drought, which I think is intuitive and California is very plugged into already, but also an increasing risk of flood that I think has been largely underestimated and I think looms large in a warming climate. So I'm going to devote some time to that now. So some of you, probably not all of you though, are familiar with the Great Flood of 1862 in California, which was this essentially flood of record for the past couple centuries in this part of the world that greatly exceeds anything that's happened in the 20th or 21st century. So there's no living memory of an event, anything approaching this magnitude. So none of California's infrastructure has ever been tested against something like this. Much of California's infrastructure was not designed for something like this. But it's thought that floods of this magnitude occur roughly every 200 years. It used to be thought that they were much rarer than that, but it turns out that there had been some underestimations of the frequency, which have been sort of rectified by looking at river sediment and flood deposit records, which happen at least 4 or 5 times per millennium of the same magnitude that happened in 1862. So that's where the 200 years comes from. But it may not be 200 years anymore, as I'll get to in a moment. A modern day repeat would, I think, pretty obviously be devastating for California. And this is something that we're actually working on right now as part of the ArcStorm 2.0 scenario with working groups from a bunch of different institutions, spanning the different University of California campuses, as well as the USGS and the Desert Research Institute, with quite a few collaborators actually. This project's gotten a slow start, but we're just getting off the ground now. But what our existing work has already shown, based on climate model simulations for the next few decades, is that there's something like a 50-50 chance of a modern recurrence of an event of this magnitude, not over the next century, but just over the next 40 years. So that's well within planning time horizons, well within, in a lot of cases, a lot of people who own homes today will still own that same home statistically when this event occurs. So this is something that I really think does need to be on people's radar more than it has been. Understandably, there's been a focus on drought and wildfire because we've seen a lot of that recently. This is a risk that I think has gone largely underestimated. And the reason for this increase in projected frequency of extreme floods and the risks associated with them mainly come from a more intense version of a very familiar historical pattern, these strong atmospheric river storms. And in some work that we did last year, my colleagues and I at UCLA and UCSB took a look at the most intense atmospheric river storms. So not the typical weak ones, but the very most intense ones, with the ones for which there are very few precedents within the past century, just a handful of individual storms that reach this threshold. And what we found is that those storms in particular, the very most intense atmospheric rivers, are likely to increase in strength by a pretty considerable fraction in a warming climate, mainly due to the direct influence of increasing atmospheric water vapor. So atmospheric rivers are really these corridors of extremely concentrated atmospheric water vapor moving at a high velocity, pushed by strong winds, and they sort of attach themselves to other kinds of storm systems. But the fundamental process is a lot of water vapor moving very fast over your head and getting squeezed out very efficiently when that water moving fast over your head hits the coastal mountains or the western slope of the Sierra Nevada or the transverse ranges in Southern California, one of these three. And this same mechanism works the same in the future. It's just that if you add a bunch of extra moisture to that air slamming into the mountains, you're going to get a lot more water falling out of those clouds. And so what we foresee is the occurrence of eventually of historically unprecedented extreme precipitation events resulting from these increasingly extreme atmospheric river storms. And so for all of these reasons, I think California flood risk looms large, partly because the thermodynamics suggests that it's going to get worse before it gets better, but also because, and again, I just wanted to reemphasize that I think there's been sort of a public underestimation because we've been dealing with such terrible wildfires and so much drought again this year. We shouldn't forget about the other side of the hydrologic coin, because eventually it will flip, and the evidence suggests it will flip sooner rather than later, perhaps in the middle of a drought. There's no reason why a drought is necessarily protective against this kind of flood event if you get a big enough sequence of storms in any given winter. But climate change is likely to increase flood risk, the risk of extreme flooding in a lot of regions, but California is actually a hotspot of potential future flood risk exposure, according to some other work that we've done recently, which is a little bit surprising. California is actually potentially at greater risk of large increases in population exposure to flood hazard than is the case in some places that are actually already really wet. And I think this is partly because there's a lot of people who sort of have been able to place it out of sight and out of mind for the past half a century or so. We shouldn't be assuming that that's going to hold forever. And I think one of the big questions is how California's flood protection infrastructure will fare in a quote unquote mega storm scenario, like a repeat of 1862. We have some recent failures to point to. The Oroville Dam spillway and the subsequent emergency there is a dramatic example, but the Army Corps in Southern California has recently announced that some really critical dams that are above major population centers in quite urbanized areas are potentially at risk of structural failures during a sufficiently large storm event. And I think a lot of this sort of made it under the radar when it happened, but back in that really wet winter just a few years ago in 2016, 2017, there was a severe flood event in South San Jose. Not, again, a place that most folks think about in terms of severe flood risk, but there was a levee failure during the severe storm events during that period. So it's quite clear that when tested, our flood control infrastructure is not always going to be up to the task. And so I do think we need to be thinking about the potential for these low probability, but really high consequence outcomes on the wet side of the precipitation distribution with respect to flood risk as well. But I do want to focus on, I think, what is probably the most immediate concern for a lot of folks, because we're entering yet another fire season that looks like it's going to be significantly worse than average. And I just want to back up for just a moment and just sort of emphasize once again that wildfire is fundamentally a natural process, and that susceptibility to wildfire is a function not just of the climate conditions at any given place at any given time, but also of the vegetation conditions and the ecosystems that exist in a particular place. And all of these things are potentially not fixed in time. Climate obviously evolves over time. Weather certainly evolves from day to day, but the plant types and the ecosystems that exist in a particular place can also shift over time. And as the climate warms, we are likely to see some of these ecosystem shifts as well. And it's also important to understand that not all wildfires are created equal. We're used to these dramatic imagery of walls of flame on the evening news, but actually that's not how a lot of fire behaves most of the time. Those are the ones that are causing most of the harm to populated areas and to ecosystems. But a great majority of the fire in general that occurs on the landscape is actually at a much lower intensity. And so there's a real range in the level of literally the temperature at which fires burn at, which has major implications for the hazard to benefit ratio that can result from them. And yes, fires do result in major ecological benefits because there are ecosystems that are either fire adapted, in which they can tolerate fires, or even fire dependent ecosystems that essentially require some frequency and intensity of fire for their survival. So these are not inherently dangerous, scary phenomena. It's just the problem is that we've seen some really bad ones recently, and I'm going to talk some more about why that's been occurring. California has seen what is, I think, an arguably dramatic increase in wildfire severity or risk in recent years, almost regardless of how you define it. There's been a large increase in the amount of acreage burned, although I think that's arguably the least relevant statistic. I think from a lot of practical perspectives, the most relevant information is the fact that 15 of the 20 most destructive fires in terms of how many homes and structures were destroyed have occurred just in the past 6 years. And also 7 of the 20 deadliest fires. And so those are really the two most frustrating statistics to see continuing to escalate in the recent years. And to see, 5 or 10,000 homes burned in a single fire is not something that we used to see in California, but we've seen it on multiple occasions over the past few years in different parts of the state. And I think just for perspective, more people have now died in California fires in the past 36 months or past 40 months, I guess, as of this presentation, than have died in earthquakes in California, in any earthquake since the Great Quake of 1906. So this really has become sort of the major disaster of modern day California, and for good reason. I mean, it's there's a lot of competing narratives out there, but I think it's quite clear that the level of destruction and harm to human life that's occurring is really it's an alarming escalation in a relatively short period of time. So what's driving this? I just want to point out that these pillars are relevant certainly in California, but also really throughout the American West. And it's really multifactorial. There isn't one singular reason why this problem has gotten so much worse recently. But I just want to go through 3 of them and then focus on the third, because of course I am a climate scientist. The first is this idea that there are just more people and more stuff in harm's way than there used to be. We've expanded cities and suburban and semi-urban or semi-rural areas where people build their homes into what's known as the wildland-urban interface to an increasing degree with each passing decade. So there, on some level, there are just more structures in highly flammable locations that are prone to fire than there used to be. That is a big part of the reason why we're seeing so many more structures burned and so much more harm to human life. Another aspect of it, and this relates both to the amount of acreage burned and the intensity of the fires to a certain degree, is the legacy of 20th century total fire suppression policies in forests specifically. So not all wildfires in California are forest fires, but a lot of the ones that have been at pretty high profile are at least partially forest fires recently. And really what's going on here is that for the better part of a century in the United States and in California, we extinguished essentially all fires that occurred on the landscape as soon as possible, which really removed a lot of the beneficial lower intensity fires that would have naturally otherwise occurred in the landscape. And this has resulted in sort of unnatural fire regimes and an accumulation of very dense forest vegetation in some places to a much greater degree than would have been the case otherwise. And so this has led to more fuel loading, as it's known in the forests, and potentially higher fire severity. But both of those two initial pillars are important, but only relevant in specific places. Obviously, urban expansion is relevant in places where people live. Fire suppression legacy is relevant primarily in forests, and not all of California's fires are forest fires. What is prevalent across the landscape, though, and acting to multiply both of these, is climate change, which is acting pervasively across the landscape. Every part of California and every part of the American West is warmer than it was a few decades ago. So I just want to go through a couple of the more specific aspects of why this is happening. So really, it's intuitive, which is to say that as temperatures increase, that the atmosphere is becoming thirstier. Literally, it's this idea of aridification. And so really what's happening is as temperatures are rising, the gap between how much water is actually in the air as vapor and how much water could be in the air is widening. So there is increasing a gap between how much water is actually in the atmosphere and how much could be in the atmosphere. And what that means is that there is increasing demand for water, not just among plants, but also in the atmosphere itself. So the atmosphere is increasingly acting as a giant sponge. Climate change and warming are effectively increasing the propensity for atmospheric sponginess, if you will. And so what we see, partly as a result of this, is that around 50%, or maybe even more, because this is a study that's from about 6 or 7 years ago, 50% or more of the observed increase in Western US forest fire acres burned is directly attributable to this warming effect so far. And in California, it's the numbers are a little bit less clear, but it's probably on that order, if not larger. And so what we have found recently is that one of the main reasons for this is that climate change is essentially making wildfire burning conditions more intense and occur more frequently. Not necessarily increasing the number of fires. In fact, there hasn't been an increase in the number of fires in California or really across the West. What we have been seeing is an increase in the severity of those fires. And so what's happening in California is that essentially what's known as extreme fire weather, so it's what you'd expect, it's the hot, dry, windy weather, has doubled in frequency in the autumn in California over the past few decades. And climate change is therefore changing the preconditions necessary for extreme fires in this part of the world. And why? Well, it's mainly the warming and the drying that results from that warming that's preconditioning vegetation to be much drier and to burn more intensely when a fire does come along. And fire is an inherently non-linear process. Fires burning more intensely doesn't just mean it burns hotter, but it means it exhibits more extreme fire behavior. They're harder to fight. They start to generate their own extreme weather conditions, like we saw this past summer with fire-generated lightning, fire-generated tornadoes, even in 2 places in California. These are the kinds of things that start to occur more frequently when these fires become large and burn at a very high intensity. And the other thing that's happening, in addition to warming, is, as I mentioned, this shift in seasonality. And in the autumn, it's even more important than in the spring, because as anyone in California knows, at the end of the long, dry summer, as you head into autumn, vegetation is at its peak seasonal dryness. So if you extend the dry season by even just a month, by delaying the rainy season by a month, which is what we've seen over the past few decades, about a 30-day delay in the rainy season on average, then you increase the overlap between extremely dry vegetation season and offshore wind season, or Santa Ana or Diablo wind season. And those are the winds that often drive many of California's most dangerous and destructive fires in September, October, and increasingly into November as well. But historically, sometimes those winds would occur after we'd seen a significant amount of wetting rainfall that would have greatly mitigated the fire risk or the severity of the fires that would have occurred during these wind events. Increasingly, we don't get those mitigating rains early enough to be helpful with respect to the first half of that offshore wind season. And so that's sort of a double whammy effect there. Not only is the vegetation drier for longer, but we're also increasingly keeping it drier longer into offshore wind season. And so all of this, I think, amounts to what I believe Jerry Brown termed a new abnormal for California, which is a term that I like because it specifically differentiates from a new normal. New normal suggests we've reached some new stable plateau, whereas really we're still on this roller coaster. it's going to continue to get warmer in California, but we don't know how much, because it's really going to depend on public policy decisions that are made over the next decade or so. We still are very much in control of how much warming eventually occurs. We know there will be some additional warming, but we don't know yet if it's going to be a modest amount or a very large amount. And really the possible outcomes span that entire range. And so the climate component of wildfire risk in California probably will get worse before it gets better. And there's a lot of follow-on implications to that. And I just wanted to emphasize that, this is not just a California problem. And just to illustrate this is footage that I took of a large pyro vortex, or sort of a fire-induced rotating column of smoke and wind in Colorado in October, just last year. And I think what this really illustrates is that we're seeing aseasonal and really extreme fire behavior in places and at times that were historically would have been essentially impossible. I mean, this specific example is a place where we're seeing really extreme fire behavior at a time of year when there would normally be snow on the ground. So this is not typical for the interior West. And so this is an accelerating catastrophe, right? This notion of increasingly devastating fires in what's known as the wild and urban interface. But it's not an inevitable crisis. And I think this is something that's really important to emphasize, is that wildfire itself is not the enemy. It's not inherently bad. It's really the intersection between these fires and populated places that's the problem and is causing all of the harm. And so, the question, I think, in my head and in a lot of people's head right now, I think we may hear more about this tomorrow, is how do we decouple the fires that we are seeing, the increasingly severe fires that we're seeing, from catastrophe? Because one does not necessarily have to follow from the other, and there are a lot of things that we can do about that. And so, I think this sort of, just to sum everything all up, not to put too fine a point on it, but to cope with this increase in extreme weather events in a warming climate, we're going to have to be really flexible. We're going to have to use climate adaptations that themselves allow for increased flexibility rather than less flexibility, because the physical reality is that we're going to see an increase both in precipitation intensity and overall aridity. So a decrease of snowpack with a longer and more intense fire season. But the question in my head, and the question that I'm pursuing now with a lot of my colleagues, is, can we actually mitigate some of these risks? Can we mitigate the risk of flood and drought simultaneously by using flood flows to recharge groundwater aquifers, for example? Can we fight the bad fires, the ones that burn people's homes down and kill people, with good fires, ones that mimic a healthier ecosystem and more natural fire patterns that help improve ecosystem health and also reduce the risk of catastrophic fires later by thinning out some of those vegetations, those regions that have become unnaturally dense, all while offering, as I mentioned, environmental co-benefits along the way. It's becoming increasingly clear that I think our historical paradigms and our management practices probably aren't going to cut it. I mean, I think it's clear that they already aren't. And we're going to have to do a lot of these things differently. So just to close officially, climate change has already arrived in California. It's no longer a projection about the future, but it's a lived reality today. And the climate today is different than it was in the 20th century, when most of California's public policy and infrastructure were developed. And so a plausible trajectory in California is that it will, of course, be warmer year-round with less snow and more intense fires, but also with less frequent storms, but very possibly much more intense storms. So an increased risk of flood on the other end of the distribution as well. And so with these increases in fire and flood risk, the question, I think, then becomes, how do we decouple these increasing risks from the harms they cause to humans and to the broader environment? And I think we can do that, but it's going to require thinking differently. And so staying flexible, I think, in the face of these increasing extremes, and thinking about climate adaptations that can maintain our resilience, not just to one end of the spectrum, but both ends, drought and flood, fire and its absence, I think, are going to be really important. So with that, I'll close, and I'm not quite sure what the time is, but hopefully we have some time for questions now, and I know we're also going to have time at the end of the series tonight.
You did great, Daniel. You ended right on time. So
perfect.
If you could stop your screen, well, you could leave that up will unmute Sabrina.
Hi. So thank you, Daniel. You ended on an up note there. We've got some really great questions that have come in, so let's jump right in. So Brad Stewart asks a Northern California question. As per your work, atmospheric river wetness will increase and flooding along with it. What about winds? Big storm winds cause vortices in ocean-facing canyons. A windy storm in the 80s brought down ancient redwoods and snapped Doug firs. Can we expect worsening winds along with higher rain volumes? And I will just say I am very interested in understanding more about wind dynamics too.
Yeah, that's a good question. And it's a question that I actually can't give a direct answer to because I don't think anyone's done the research yet. I think it's plausible the answer could be yes, although I wouldn't expect it to be as big of an effect as the moisture increases. So off the cuff, maybe yes, but probably by a small amount. And it's probably a less consequential increase than the moisture increases we would see during the strongest storms. But that's an interesting question because the moisture increases actually can factor into wind changes. Because if you have moisture storms, the latent energy, in that moist atmosphere can potentially lead to stronger storms, a stronger wind. So, but that's a maybe, I guess I would say.
Yeah,
We'll
it's
see.
hard. It's tough. We had a really dramatic wind event in Pasadena in, I think it was about 2009, and I hadn't seen anything like that in Southern California, so it was interesting. And it wasn't raining. It was primarily just a wind event. So something else to look forward to. Okay, John asks, a couple of centuries ago. Sorry, it just moved. A couple of centuries ago, California, particularly Southern California, underwent a 150-year-long drought. Should we anticipate any such era in the next years?
Well, one of the issues is what is drought, first of all, because everybody who deals with drought has a different definition. And I think that something I didn't emphasize as much here is that drought in California is likely to increase by a lot more than the changes in precipitation would suggest. Why is that? Well, because of rising temperatures. And so, in fact, arguably, very warm temperatures become a key driver of the increasing severity and frequency of drought in not only in this part of the world, but more generally. And there's a lot of scientists who are currently arguing that the American Southwest, in a broad sense, is currently experiencing a mega drought. It's not because precipitation is at unprecedented low levels, although it's lower than average. It's because temperatures have been at unprecedented warm levels combined with relatively low precipitation. So it's actually primarily the warm temperatures that are driving that. And there's a lot of research that kind of suggests that isn't likely to really reverse itself this century. So is it drought, or is it something that folks are increasingly calling aridification because it's more permanent? Yeah. And even a wet, even an increase in precipitation for a few years won't dig us out of that long-term deficit. I think that yes and no, with the caveat that it won't be a 150-year drought in the sense that there'll be no precipitation for 150 years. If it's droughty for that long, it'll mainly be because it's much, much warmer, punctuated by occasionally very wet spells that aren't enough to overcome those warmer temperatures.
It's just something that I have noticed in restoration ecology. That's a question we're not asking often enough in this drive towards reforestation post-fire.
I mean, this is a big question that I've
had. Yeah.
I mean, I've had that question for ecologists recently, and I don't think anybody has a great answer to it because a lot, initially folks assume, well, yes, this is a fire resilient species. They always grow back after fires.
Yeah.
But really what the actual truth is, they always grew back after fires in our historical climate. It's not always clear that will necessarily be the case in our new 21st century climate.
Yeah. Okay, another question about wind. Mimi Enright, hi Mimi, who is our Master Gardener Coordinator actually in Sonoma County. she'll yell at me if I got that wrong. It seems that we're experiencing more winds in Northern California. What's forecasted for wind? We talked about that a little bit. And same question for fog. A lot of fog dependent coastal systems up there.
Yeah, two good questions. The wind question, I kind of answered the winter version of it, but I suspect what you're actually saying is that you've noticed more wind in autumn when it's really important for agricultural or wildfire considerations. And I was actually just having a conversation with a colleague who's about to embark on that research project to answer that more concretely, because his perception is also that there has recently been more wind in autumn. So the anecdotal evidence seems to say yes. It's not totally clear whether that's actually a climate change signal or not, though. It's not actually clear that climate change should necessarily be expected to increase autumn winds. We see this sort of in our fire weather studies, where the main reason why the fire weather index increases so much in autumn is just because it's so much drier and hotter, but not so much because the winds are projected to increase necessarily. But that's a bit of an open question that I would lean towards, again, maybe to yes, at least in terms of what we've seen, not necessarily whether that will continue. On the fog side, I hate to hedge again. I think a lot of the reasons that people are asking these good questions, and they're the hardest questions. It's a lot harder to address these than some of the broader temperature and precipitation questions. The fog question is interesting because, all of California is getting hotter in the summer, except maybe the immediate coast. And I mean like the immediate coast. Why is that? It's because the ocean is so cold on the California cold current. The immediate offshore waters are nutrient rich and freezing, especially if you're off the coast of Northern California. And so that engenders a really robust marine layer. Even if it gets a lot hotter in Sacramento, what that can do is actually just increase the strength of the sea breeze. So it can actually increase the strength of the marine layer, draw fog further inland to a greater degree. So you actually have a greater contrast where it gets super extremely hot in the Central Valley and then maybe doesn't warm as much all the time along the immediate coast. On the other hand, we've seen a lot of record heat events along the immediate coast the last couple of years. I mean, we've seen like 110, 115 degree temperatures in some places along the California coast, especially in Southern California, like right up within a mile or two of the beaches. And so certain types of heat waves are probably going to produce increasingly extreme temperatures everywhere. But the more run-of-the-mill heat waves are probably going to increase a lot more inland than the coast because of this marine layer effect. So what happens to the fog overall? I think it's still a bit of an open question because we don't know exactly what's going to happen to the California current.
Yeah, of course, for those of us who live along the Santa Barbara Ventura coast, we're not prepared for this kind of heat wave. We don't have air conditioning. So, there's sort of that human dimension of how those factors are going to be felt.
Yeah, and that's a big problem. Even if and this is sort of interesting, this dynamic may play out this year where the ocean is pretty cold along the coast right now. And so the early season heat waves probably won't be very severe along the immediate coast, even though they may be much more severe inland. But the autumn heat waves, you lose that protective effect because you have offshore flow, the ocean isn't as cold, there isn't as much upwelling. So I would expect those autumn heat waves to be the real killer ones along the immediate coast because you lose that protective effect of the marine layer.
Yeah. Okay, moving on, we've got Sherry. Do we just have like 1 more minute for questions?
Well, we could take the rest of the questions at the end. Sarah May, if that's to start at 5:05.
Should I ask 1 more now? Or?
Sure, a short one, Daniel.
Okay, I think this will be short for you, Daniel, actually. It's kind of a clarification question. Are the atmospheric river storms the same as El Nino and La Nina? And if not, how will the El Nino La Nina situation change with climate change?
Oh boy, there's a lot in there. But I can try and be quick. Atmospheric rivers happen every year. We even had them this year in this crazy drought year. That was a La Nina year. We tend to also see them in El Nino years. La Nina, El Nino are really just different phases of what's more broadly known as the El Nino Southern Oscillation. It's just a seesaw pattern of ocean temperatures in the tropical Pacific Ocean. La Nina is cool water in the eastern tropical Pacific. El Nino is warm water in the eastern tropical Pacific. And it does affect California weather, especially when it's in its very strong phase on either side. If it's weak, it's kind of equivocal. They do tend to modulate the frequency of atmospheric rivers, but we tend to see them every year, irrespective of El Nino or La Nina. And in the future, there's some evidence that the cycling between El Nino and La Nina may increase in amplitude, but not in frequency. So we may see more extreme La Ninas, more extreme El Ninas that could partly be driving this increase in whiplash that I was talking about.
Interesting. Okay, well, thank you so much. And I look forward to having some more discussion at the end. But right now, I'm happy to introduce our next speaker, who I had the pleasure of hiring, actually, Sarah May Nelson. Sarah May is a climate change communication specialist and the academic coordinator of our new UC Climate Stewards program, which will be rolling out around the state this year. She also works with the National Network for Ocean and Climate Change Interpretation and the UN Education, Communication, and Outreach Stakeholders Community. So, Sarah May.
Thank you so much, Sabrina. Hello, everyone. It's great to be with you all this evening. I'm going to turn my screen sharing on so you can learn a little bit more about the course that Sabrina alluded to. So I do work for the University of California Naturalist Program, which is part of UC A&R. And a couple of years ago, our naturalists kind of spoke up and said they wanted to learn more about climate change. And that led to a process where several people got together and said, how do we do this the best for our alumni? What they realized is it wasn't just more information in their existing course, it was actually to move forward and create an entirely new course. And so I was hired on, as Sabrina said, 2 years ago in 2019 to put together this course. And I'm really glad that I get to go after Daniel. That was just such great information, and it really emphasizes the things that Californians really care about: precipitation, drought, wildfire, flood. And y'all want to know what to do about it. And the Climate Stewards course is exactly that. It's about how can we foster resilience in our communities and our ecosystems to these impacts that we're anticipating. So the UC Climate Stewards course, our mission is indeed to prepare climate stewards, which are Californians, to communicate and engage in local efforts to advance climate resiliency in community and ecosystem spaces. And our vision is to one day have a California that is prepared for these eventualities as we experience wildfire changes, as we experience things like COVID, because our current situation with the virus is tied back into some of those changes that Daniel referred to in terms of precipitation and drought and fire. And so we designed this course to help our students not just learn about the science, but to learn about their communities, to learn about relationships, to learn how to go into those spaces and to really make a difference, maybe in the infrastructure or in the availability of food or how water was being used in their communities. And it's just been such a great opportunity. Over the last few months, we've initiated our first courses. Our pilots ran at the end of 2020. We've had several courses that have already run this year. And I just want to give you a little bit of an idea of how our courses do in fact run. So right now we are completely virtual since we, as y'all know, are sheltering in place across much of the state. And our class was actually designed to exist really strongly in this virtual realm. It is a hybrid class. So we do have a handbook that is read, preferably before the course, if that is an option for our students. We then have online material in a learning system on the computer. And we put all of our content there so that when we get together in either in person in real time or in a virtual space such as we are in right now, that we can have discussions, we can have deeper analysis and application of the content that we've learned to try and take our knowledge and learning to the next step. We also have some great field trips and field work that happens, as well as our students participating in just some incredible capstone projects. And I know some of our climate stewards are here today with us, and I just want to say just the incredible work that they're doing ranges from changing their home water usage to developing fire resistant plans for their neighborhoods, to actually going to homeowners associations and talking about how they can prepare their neighborhoods for our changing climate conditions. So it's really incredible what our students are doing. And last but not least, after they graduate from the course, they are going into those communities and doing volunteer service and joining our community of practice, where our students from across the state can get together and have conversations, as well as support each other and build on the work that's being done maybe in a Northern California community and extend that to a Southern California space. So just to give you a little bit of an idea, here are some photos of our climate stewards in action. Everything from being in the field to being in their virtual classrooms. They are experiencing everything from touring wind farms to going into places like Tamales Bay to learn how the changing chemistry of the ocean is impacting the animals that live there and how that's impacting aquaculture farmers. They're also going into spaces and learning more about climate smart agriculture, or they're going into places and helping to reduce growth in spaces where they're helping with fire resiliency. So it's really amazing what the work of our students is already doing. We've been running our courses for 6 months, and we're already seeing changes in communities as they begin to adapt and work to mitigate their carbon dioxide emissions to reduce their personal and community impacts on our changing climate. Just as Daniel alluded to, we have time to make a difference, and those differences are totally dependent on our choices. And it's just incredible what one person who is passionate about making a difference can do to stimulate decision-making in their communities. So I mentioned that we do have a course handbook, and that is Climate Stewardship, Taking Collective Action to Protect California. This was written by Adina Marinlindler with Brendan Buehler, and it is a book about stories of positive change that is happening in our state. It's happening now, and it's been happening for 10, 20 years already. And this ranges from the work that's happening within our cities to the work that our tribal communities are doing, from the work of youth, from the coast to the mountains. And this is the only required reading material for our course. We do have several other suggested or recommended reading items. The highly recommended reading, The Thinking Person's Guide to Climate Change, that's edited by Robert Hansen. And for myself, as a climate change communication specialist and educator, it's the best kind of one-stop shop book that I have found for seeing the picture of what's happening, what we can do, and the way it's written is in a very accessible manner for just the wide variety of people in our communities. So as I mentioned, the course was put together by a team. We did have a steering committee that put this together, and the course was founded with a set of guiding principles. And I want to share those with you because they are truly what makes our class different from other climate change courses that are out there. So our guiding principles really start, as I mentioned, with our mission, looking at community and ecosystem resilience. But even more deeply, we extend to talking about systems. And as we've learned, again, during the COVID-19 pandemic, our systems have problems. And when we address the root causes of the issues, we have the opportunity to make changes, not just in one area where there might be problems, but across a range of areas where people might be disadvantaged because of the color of their skin, because of their income level, because of the location where they live, whether that's in an urban area or rural area. So systems thinking is a critical principle that we use to guide how we put together the course. We also, being the University of California, are very deeply grounded in science and very particularly interdisciplinary science. So we're not just looking at natural sciences and climate, but we are very significantly looking at social sciences, how education is involved, how the different science silos come together and begin to interact in this very interesting world of climate, not just the changing conditions, but also the social issues that have arisen because of the experiences that we're having across the world. One of the other things that makes this very unique is that we are addressing the whole person. So our course isn't just about knowledge, it's about you and how you are interacting with our changing lives. We want you to know the science, but we also know that really that only addresses what might be happening in your mind. And we are experiencing changes in our physical health. We're experiencing changes in our emotional and mental health because of things like the wildfire, extreme weather, and flood experiences. And we're also experiencing our own relationship to place and home changing. So we really want to emphasize that we as humans are connected to the entire community of life. It's not just about us, it's about everything that exists here on the planet that we are just one small part of. And I'm going to talk to you a little bit more about how we bring that forward in just a moment. And also, as I just mentioned, we are really focusing on local. You may have heard the phrase, think global, but act local. And what we know is that's very true. We can make changes happen in our communities very much more quickly and much more significantly to our homes, our neighborhoods, our businesses than we can if we're working on like a national or international level. We also really emphasize the need to be positive. You know, what Daniel shared with us was incredible information, and it can be a bit overwhelming sometimes, but we need to take that information in stride and understand what science is showing us is a variety of information and a variety of options. And if we go into this work looking at it from what we can do and how we can make things better, it really significantly impacts our ability to move forward. We also are working very diligently to address issues of inclusivity, equity, and justice. We know that climate change is really a multiplier of injustice, and the people that are experiencing the worst issues are the ones that are least able to deal with it and who are already experiencing some of the biggest systemic problems that we have here, not just in California, but in the United States as well. We recognize that there are many ways of knowing and being, and that, you know, there isn't necessarily the one exactly right way, that we have a lot of opportunities and options to move forward. And so we want to recognize that we do have a lot of knowledge, very deep knowledge and very connected knowledge to our places and our communities that we want to bring forward in this space as we learn together. One of the things that we know as well is that when people can participate in science, they can feel much more able to make changes. And so we really emphasize a lot of work in the participatory science sphere. You may have heard of participatory science referred to before as community science or citizen science. And we choose to use the term participatory science really to make it more inclusive, but also to emphasize the fact that we are partaking in this effort together as community members with the people that are doing the science as well and writing the journal articles and getting them published. And last but not least, we have a really robust community of practice that we are connecting to and moving forward with, and really helping people to experience things in a bit of a different way. So our key concepts and themes, we really look at social emotional resilience and trauma-aware education and communication practices. We recognize as part of that whole person, it's really critical to bring that into our spaces. We are also really emphasizing the different things that we can do throughout the course itself, and as we learn together, what just our opportunities and possibilities are. So we have 6 units in the course that range from connecting with community to connecting with each other, to working in the community resilience space, and also learning the science. It is not the most important thing I would say that we learn, but it is one of the things that people are most interested in learning. And this is a lot of information. I'm not going to read through this slide in detail, but we have a lot of opportunities in Southern California. That's where our largest number of partners are. And there's a lot of chances for you to become part of our community of practice in the coming days. So I hope that if anyone has interest or questions, that you will reach out and become part of our growing community who are working toward resilient and healthy ecosystems and communities in the face of climate impacts. So I think that's my time, and I'm going to stop sharing my screen now.
Thank you, Sarah Mae. So we have some questions here. I do want to ask, and maybe someone from the program support unit can look for this. I don't think that you ended with a link to Climate Stewards.
No, I didn't, so because I have to put it in the chat.
Okay, good. Okay, yeah. If somebody else could drop that into the chat, that would be fantastic.
We'll find that for you.
Thank you. Yeah, it's on the CalNat webpage, Sherry. Okay, well, Sarah Mae is answering some other questions. So one question, the first question I think that came up for you, sorry, I'm scrolling through questions for Daniel as well. I did want to mention that there was a question from Lynn Rodriguez. Hi, Lynn. And about whether the Climate Steward, how to get involved in the Climate Stewards program, whether the handbook is available for people who aren't students. And I know the answer to that, but I'll let you answer that. I did want to say, Lynn, I would love to continue the conversation with you and myself and Annemiek and Sarah Mae about bringing Climate Stewards to Ventura, but it will be coming to Santa Barbara this spring.
Yeah,
well.
So the Climate Stewards Handbook will be available to anyone. It's being published as a trade paperback, and we're just in pre-order right now. So we just got that this week. So that will be coming out, and you can find it at a book dealer near you in the next couple of months. If you want to find out more about courses near you, how to potentially work with becoming a partner to offer the course or an instructor to offer the course, you can check out the link that Sherry just put in the chat. So that's the California Naturalist webpage with the Climate Stewards page itself. We've got some frequently asked questions and other information there as well. And yeah, we've got some active courses that are happening all around, and we've had a few discussions about bringing it more to Ventura. So we'll move those forward in the future.
Talking about that. Wonderful. There's a couple of questions about whether you're collaborating with UC Master Gardeners or whether there's an opportunity for Master Gardeners to get the same information.
Yeah. So the California Naturalist program is almost like a parallel program to the Master Gardener program. So our certified naturalists are very similar to certified Master Gardeners. So Master Gardeners throughout the state are welcome to take the course, just like you would take a California Naturalist course or a Master Gardener course. We have had a few conversations with Mimi and others about how we can kind of make that relationship a little bit closer, but we haven't fully realize those possibilities quite yet. The conversations are continuing.
And just, I noticed in the chat more questions about the book. It is published by UC Press. So if you go to their website, you can find information on how to pre-order, or you can sit tight for another, say, month, and then it'll be available on Amazon or Barnes & Noble or, many places. Okay, thank you, Kim. All right. How are the students selected?
Oh, that's a great question. So the students reach out to our partner organizations. So for instance, one of our partners in Southern California who will be running a course in June is University of Riverside Palm Desert Center. And I know a few of our Climate Stewards graduates from there are here tonight. So you would reach out directly to the partner through the link on our webpage, the Climate Stewards webpage. And basically you submit a very basic application to them. And it's essentially a first come, first serve basis with a few maybe minor tweaks depending on the partners themselves. Our partners make the choices who they accept, and a lot of times it's related to space. So the general size of the classes may be 20 to 24, and we are working actively to get more classes up and running. We are having another instructor training in October, so the next set of partners will be able to train will be coming up then.
Great. Sorry, I was putting in the course survey here. You can, there's been a lot of other questions about how to stay abreast of things and how to contact you, Sarah May.
Yep.
And one of the things that you can do is add yourself to our listserv for the UC Climate Stewards program. So if you go to the Climate Stewards page and scroll down, you'll see a link to adding yourself to the listserv. And thank you, Sherry. All right. So here I'm going to sort of end us up on this question right here. And then there's a bunch more questions for Daniel as well. But this one I think is for both of you, possibly. Given wetter wet and drier dry, how can UC educate the public, including the environmentalists, that water storage can mitigate the effects on agriculture and urban communities? Would not many small reservoirs widespread over the state be more valuable than a few huge storage areas?
Well, I know a few things about that, but I suspect Daniel knows more. So I'll very quickly say that that's part of what Climate Stewards is about. If that is of interest to you, we work to give you the information to empower you to work in your community, to bring that sort of information forward to your representatives, to your city councils, to your county water districts, to see how you might be able to implement those sorts of measures in your own spaces. That's part of what we teach within the Climate Stewards course.
I would say county water districts and also groundwater management agencies are a really important role here. Daniel, do you want to sort of take a stab at the technical part of that?
Yeah, I mean, I think that it's tricky because we have water systems in California that are essentially predicated on a very particular historical climate, which is that, you know, it rains in the winter and then in the mountains it snows in the winter, and very slowly throughout spring, the water melts, replenishes the big, large western slope reservoirs we primarily rely on, and we go from there. As all of that gets disrupted, that system is definitely not going to function as designed. So the question about what to do about it is challenging because, you know, on the one hand, you do want to have large increments of storage that can get you through multi-year droughts. But on the other hand, those also become liabilities in the climate that we expect to see in the future, which is much less snow, much larger flood events. And so I think this partially addresses another question I saw in the Q&A. You know, there are flood risk mandates in a lot of California's major reservoirs, some of which are designed primarily as flood control structures rather than water storage. Water storage, in some cases, is a secondary role, or at least it's in there somewhere. But most of California's major dams, you have to maintain safety margins during the wet season so that if a huge storm comes along, you have enough space to let water leave the dam so it doesn't get overtopped and overflow, because there is a maximum rate at which you can let water leave the dam, usually with spillway or the pipes or whatever it is. So the big dams become a liability for two reasons. One, in an increasingly warm and water scarce world with less snow, you don't get that seasonal replenishment that you used to, so you can't rely on that. And also, when it is really wet, you're not really able to capture any additional amount of water behind those dams because you still have to keep that safety margin. So you still have to let a lot of that water go anyway in the big dams. So there is some argument for more distributed storage, but there are, you know, but exactly how you implement that is a big question. And it doesn't necessarily have to take the form of lots of small reservoirs, because there are a lot of practical impediments and environmental reasons why you might not want to do that. A lot of times it's going to come down to groundwater and strategically using land to recharge aquifers, sometimes using the floodwaters themselves. flood managed aquifer recharge is actually something that the Department of Water Resources is seriously pursuing. I would argue maybe not on the scale that they need to be, given the magnitude of the future changes, but it is something that was not really talked about just a decade or so ago and is definitely part of the conversation now. So I think that's a promising development. And I really think that is kind of the way of the future, being much more circumspect about groundwater and actively using it as a resource, not just saying we shouldn't be pumping it so much, but saying how can we actually improve the situation so that we can pump it when we need to without destroying the aquifer and completely depleting it. I think that's one of the most promising avenues.
Yeah. One interesting thing in the San Gabriel River, and I'm sure in other areas as well, they have been starting to utilize gravel mines as sort of spent gravel mines as infiltration basins.
And so that's one of the big practical impediments is you can't always just magically make a flood go where you need it to go so it can actually recharge groundwater safely and effectively. But if we have an eye towards that, if we sort of redesign the system so that it's targeted to do that, it should be able to do that much more than it can today. So,
well, it is 7:30 now. I would like to hand the floor back over to Annemiek to formally close our session, but invite everyone who can stay to stay on for another 15-20 minutes so that we can address some more of these wonderful questions.
Sabrina, it's 5:30 in California.
Sorry, I guess now I'm not really at Emma Woods. Sorry.
Yeah, so Sabrina is in Oklahoma right now. So thank you very much. I want to thank the speakers, especially for very enlightening presentations, and Sabrina for being an excellent moderator. We just, to respect everyone's time, we would like to invite everyone back tomorrow at 4 p.m. For our Impact on Agriculture session. And we will continue with question and answers from here on, but we just wanted to let those go who need to go. And thank you very much, and we'll talk to you tomorrow.
Great, thank you. And thank you all of you who are staying on with us. So as Annemiek mentioned, we do have a session on agriculture tomorrow, and then a session really focusing in on fire issues on Thursday. So I may jump over a few of the agriculture related questions that have come in, but I'll work on asking the questions in the order that they came in. So scrolling back up here, Francis Fujioka asked a question that many other people may have as well, and it's sort of a clarification question. What do the scales in some of the figures of precipitation change represent? And I don't know if Daniel still has the ability to share his screen, but that might be helpful.
I think they're mostly changes in the frequency. So it's like a percentage. So 100% increase would be a doubling, for example, of the frequency. I think that's probably
some of them were also deviation from normal, and that may be something people aren't as used to looking at.
I'm not sure that I had those in this one, but maybe I'm just not thinking about the right presentation. I can quickly see if I can find anything else. Nope, I think everything was percent change.
Okay. All right. Carol asked a question that may be a little bit of a comment and a question. So what areas of Southern California are less populated and fire retarded? And I'm not sure if she means fire prone or what there, but that's sort of a land use question.
I mean, the deserts would be most fuel limited. I mean, you don't often, especially in dry years, you don't tend to see many wildfires in the southeastern deserts. Last year, that was a little bit different. The past couple of years, we've actually have seen some fire activity in unusual places. Like there were large fires in Joshua Tree, for example. That's partly because of invasive grasses that are sort of filling in the gaps between the sparse desert vegetation sometimes. So, but that's probably where there will be a lot of years moving forward where there are no major fires in the deserts. So.
Okay, this was really another comment. Flammability is not just a function of climate. In the Sierras, tree mortality from beetle infestation has substantially increased flammability of large fuels. And they do mention that the understanding that beetle infestation is enhanced by prolonged drought. But can you comment a little bit on the relationship between beetles and climate change?
I'm not a beetle expert. I don't disagree with that statement. It's clearly true. I do know that part of the reason why beetle infestations have become as prominent as they have been is because the trees themselves are increasingly drought stressed with the aridification of the landscape, and the beetles themselves. This is less of an issue in California, but it's been a major issue in higher elevation portions of the West and in Western Canada, that we're no longer seeing the extremely cold winter temperatures that would have really killed off a lot of these beetles and kept their populations down. So there actually is a climate component even baked into the beetle question, because those infestations are easier to occur in trees and in ecosystems that are already stressed. And the beetles themselves are seem to be thriving better than they used to in a climate where there's fewer extreme cold events.
Yeah, certainly there's a lot of species where we're seeing range expansions or movements into new areas because whatever were the seasonal limiting factors, such as extreme freeze, are less frequent or less severe.
Mm-hmm.
So that's certainly been a piece of it as well. Most of our, let's see, what's the next question that came in? Most of our forest areas are in some lineage with earthquake faults that are responses to the climate. Yes, no. I think the heart of that question is whether there's a relationship between climate change and earthquakes.
No, but an alternative interpretation of that question is there a relationship intrinsically between where the trees are and what California's geography is as a function of plate tectonics? The answer to that one is yes, which is also related to which places get the most moisture. You know, the transverse ranges, the Sierra Nevada, the Coast Ranges exist where they do largely because of the plate tectonics on the plate boundary, the Pacific North American plates. So, you know, California's physical geography is what it is, you know, partly for that reason. And that is to the extent that fires and climate are related to the physical geography, then you know, there's on some level, all those things are connected.
There's also the connection, not so much in California, but in the central and eastern US between sort of climate, carbon production and earthquakes, where there's a lot of fracking going on. And we certainly in Oklahoma, we've experienced some frack quakes.
Yeah, you can definitely get artificially or human-induced earthquakes in those from those injection wells.
Okay. Down here, what's your take on the California desert? Should we sell our home of 18 years outside of Palm Springs?
I don't think I'm equipped to answer the question. I mean, the desert's already a hot and dry place. It'll get hotter, but in some ways, maybe that's more manageable than it getting hotter in a place that wasn't already hot. I mean, I think this was already alluded to. There's a huge problem in coastal California in places where buildings are not designed to have much insulation. They're not designed to stay cool in extreme heat waves. And so people and structures and infrastructure are not adapted to it. So there, the same increment of warming might have a much larger downside in terms of the human health and well-being impacts of increasing extreme heat waves than it would, you know. So that might be a much bigger problem on the west side of LA or in parts of the San Francisco Bay Area than it would be in Palm Springs. I mean, that's one perspective.
Yeah, I will say that one of the things that we've been looking at in UCANR is what kinds of extension information people might need as either as the result of planned public power shutoffs, or if we start to see more stresses on our electrical system because of these high heat days. So
I just saw a clarification that the question may have been actually regarding flood risk downstream of the San Bernardinos. Well, in that case, I mean, if you're in a floodplain, I mean, so the alluvial floodplains on the east side of the mountains in Southern California, literally into the desert, a lot of the subdivisions in a lot of the desert communities are built on alluvial fans. From the name, you might guess these are large debris flow and flood deposits from geological past. So clearly floods can happen there, even though it's a dry place. And to the extent that extreme precipitation will increase in a warming climate, the risk of those sorts of events will increase. In fact, we actually saw a little bit of evidence they may increase even a little bit more than you'd expect on the leeward side, so on the dry side of some of California's mountain ranges. So that's something to think about. Although it is a risk that already exists, it's just easy to put out of sight and out of mind because it doesn't happen very often. So
yeah, I think certainly something you might want to consider in making that decision whether to move is getting a better sense of revised and updated flood maps and figuring out if you are in a floodplain. Okay, are you seeing increased wildfire risk in future years in Southern California to the same degree as Northern California?
Yes, although the one interesting exception are, as many folks like to point out, the coastal Southern California chaparral fire regime is somewhat different from most of California's other fire regimes in that it does not always have the same response to warmth and dryness. There is such a thing as fuel limited fire regimes, meaning that there actually isn't always a continuous or a dense bed of vegetation to provide fires room to move forward in all cases. And so sometimes in those places, it's actually the wet years where you have worse fire years because there's more vegetation growth, there's more contiguous uninterrupted vegetation. Most of California, the amount of vegetation is not a problem. They're more climate limited than meaning they're more sensitive to dryness than they are to the sparsity of vegetation. But in parts of Southern California, and by that I mean the non-forest parts of Southern California, there are pockets that maybe kind of have the opposite response. But in general, the reality is that the effect of warming and drying of the vegetation is so profound that under the extreme wind conditions that we get periodically in the autumn every year, in a warmer, drier climate, given those conditions, you're going to see increased fire risk, all else being equal. So even in these fuel limited places, under the right kind of conditions, climate will still lead to an increase in risk. But I do think that the risk increases will probably be highest in forested and mixed forest regimes rather than, say, grasslands or the desert or really sparse chaparral.
Yeah, and I should say I'll be talking a little bit on Thursday about the relationship between invasive plants and fire risk in Southern California.
That's a big part of the story. I mean, the fact that there's a lot of grass growing where it didn't used to grow before, and that's a big part of what's going on here.
Yeah, and a lot of what used to be sparse chaparral that no longer is.
Right.
Okay. Any thoughts on future reservoir operations and whether or not it is inevitable that we will have to sacrifice some potential water supply in order to improve flood protection?
I hope as much as I would rather not, I mean, as much as it pains me to say it, I hope we do sacrifice some of that headroom for flood control, because otherwise, eventually something's going to come along that is a catastrophe. So I'm hopeful that we do adjust that amount of requisite headroom, to that safety margin at the top of the reservoirs, because some of these storms that we see that are plausible in the future are just sort of alarmingly big. They still don't occur very often, but they're huge when they do occur. And we know that this is not some imaginary, model fairy tale. It happened in 1862. So we don't even need to invoke climate change to know that it could happen again. But what we're saying is that we actually think that instead of having, the likelihood of it happening is going way up. And so I think that we probably will. I think that is the unfortunate reality. Whether we will, though, the rulemaking is interesting. It's not easy to change the rules. There's a lot of people who don't want to change the rules because it does mean that you lose storage. So I think this notion of forecast informed operations is actually really promising. I think it's operationalized at a couple of places in Northern California right now. This idea that if you use a weather forecast, right, we actually, you don't get hit by a megastorm out of nowhere. It's not like you wake up one morning and your house is underwater. The good news is these are not like earthquakes. They are fairly predictable. We will see it coming. We'll have at least a few days, probably more like a week to 10 days of notice that something big is on the horizon, meaning that if you have flexible, again, keyword being the flexibility, flexible reservoir operations, you can keep a small amount of headroom when the forecast is dry, as long as when they say, okay, there could be a big storm next week, you have to start letting some of that water go. If the storm never shows up on the radar, then you don't necessarily have to let that water go. So that's flexibility in forecast informed operations, I think, will be a big risk reducer on both ends of the spectrum in a warmer, more variable climate.
And I do just want to add, because I think a lot of your approach to this is thinking at the state level, or maybe the regional level. I do a lot of thinking, as an extension advisor at the homeowner level and the community level. And I think going back to that question about, small reservoirs versus large ones, I think investigating things like, oh my gosh, I just had the word and I lost it. More underground storage. Sarah May, what's the word I'm looking for?
Groundwater?
Not just groundwater, like plastic things buried under the ground.
Oh, like tank systems and yeah, I don't know the word you're looking for.
There's another C word that I'm looking for, but it's something that we've looked at a lot in the Los Angeles area. Not aquifers, not the cisterns.
Yeah.
So much, Pat Pippin. Yes, and we have some really large scale cisterns that have been put in parts of the San Fernando Valley where there's a lot of flood risk and a lot of drought, a lot of dry times being experienced. And I think investigating more that sort of site-specific water storage level so that we can take some of the pressure for water storage off of the facilities that are also being used for flood mitigation. So just a thought there. All right. We're starting to get more heat events that threaten agriculture. Can you discuss that risk?
Yeah, I mean, the unfortunate reality is that one of the clearest and most unavoidable consequences of global warming are an increase in heat waves and an increase in extreme heat waves. That will continue. Yeah, it will continue until we eventually stabilize the climate. So it's, from a physical perspective, it's something that's kind of, it's going to get worse before it gets better. But the interesting thing is, as I kind of alluded to earlier, it's not totally uniform. The biggest heat increases are probably going to occur over the eastern 2/3 of California. And I know that cuts an awkward cross-section across the physical geography, but it really is an inland versus coastal difference. We may not see it as big an increase in spring and summer heat events right along the coast. But as I mentioned, I think we are going to see a big increase in those extreme heat events, even along the immediate coast in, late August through October, because that's when we have that offshore flow. We don't have the benefit of the marine layer. You're pretty much just getting the same air mass at the coast that you do inland. And so if inland's warming, then you're going to get it at the coast too. So I would expect the biggest increases in extreme heat along the immediate coast to probably be in autumn. Elsewhere in California, it's really going to be autumn and summer as well. And I think it's important to realize that aseasonal heat waves can have an even bigger impact. I mean, a 90-degree day in Central California in like December or January wouldn't be extraordinary in July or August, but in the middle of winter, that would be. And I think, especially from an agricultural or ecological perspective, it's probably not going to cause, heat illness in people because it's not that hot and the sun angle's low. But in vegetation, I mean, it could do some strange things depending on what you're talking about, especially if it's more than just a day of it, a false spring or a false summer, arguably. So some of these aseasonal events that we've been seeing recently are facilitated by the increasing number of dry days. Saw a lot of offshore flow this winter. That's partly why it was windy throughout the winter. They weren't winter storms, cold, damp coastal winds. They were like dry and desiccating and sometimes warm winds from the north and east. That the frequency of those kind of days could make a big difference too, from I think from an ecological perspective, when they occur at the wrong time of year, essentially.
Certainly, and I think there's a good point. I've done some work on the impact of higher temperatures on fish populations, and certainly you make a good point about the length of that event too, and whether it goes on for a few days, just one day, a week, can certainly really change the impacts.
And I just want to share too. So I live in Half Moon Bay, California, really coastal, really foggy. And one of the things that's really important to remember is that the definition of extreme heat doesn't have to do with a set temperature. The definition of extreme heat has to do with the degree difference. So here in Half Moon Bay, California, you know, our average temperatures in an entire year really don't exceed 80 to 85 degrees. So for us, a 90-degree day is an extreme heat day, and we can see significant impacts on human health as a result of that. So a Southern California equivalent would be something like Santa Barbara, you know, where you get kind of that coastal fog, you get some of that more cool weather. And really, that's one of the things that we need to think about in terms of our community preparedness. When we think about extreme heat in terms of agriculture versus human health, there can be differing definitions. And so that's one of the important reasons that our communities are here, right? Attending this event today to learn about that, to see how they can go and speak to their community, you know, representatives to acquire the things that people need to survive those events as well.
Yeah, definitely. Okay, and just to reiterate, tomorrow we're going to be hearing from Tapan Patak and Ben Faber talking about impacts to agriculture. So I'm going to defer a few of those questions that I know that they are well suited to address. So please join us again tomorrow. And if those questions don't get answered, ask them again. Daniel, would some of your findings for California also apply to Colorado?
Yeah, I mean, Colorado's got a pretty different climate than California. The ones that would apply, well, extreme heat increases. Unfortunately, that's pretty much universal. Increase in really extreme precipitation events, as I mentioned, is kind of universal, even in places that are, you know, maybe getting less precipitation overall. So that's also a consideration in Colorado. And, you know, the aridity-driven increases in wildfire risk are also relevant in Colorado. I mean, Colorado saw a terrible fire season last year as well as California. You know, so it's including, you know, the largest fires in modern history in this part of the world, and some of the most destructive fires. And one of the fires, you know, jumped the Continental Divide in a place where there was, I think, almost 2 miles of granite separating them. So the fire literally had to leap, you know, to spot 2 miles ahead over the divide in October. I mean, this is the time of year when there's usually a couple of feet of snow on the ground on the Continental Divide. I mean, that's up at 13,000 feet in elevation. And yet that was facilitated by record dry summer that followed it, which is more meaningful in Colorado because there's usually quite a lot of precipitation in summer as opposed to California, but also record warmth. And the use of the unifying thing is this record warmth and what this warmth is doing to the aridity in general across the landscape, across different climate zones. And this is why we're seeing sort of these increases in fire severity in a bunch of really different kinds of climate regions. I mean, we see it in California, and we see it in other parts of the West that have very different climates. We also see it in the Arctic and subarctic. We see it in Southeast Australia. All of these are places that have distinctly different climates from one another. And yet the shared reality is that the warming is bringing about increases in aridity, even though the background climatology is completely different.
Okay, I think we have time for just a couple of more questions here. And again, I'm gonna allow us to talk about the agriculture ones tomorrow. I've read about the quasi-periodic 200-year cycle of enormous California floods. I believe these are inferred from ocean sediment layers. What is our confidence level that these floods are of approximate magnitude as the 1862 flood or even larger?
Well, I'll go backwards. There's a lot of evidence of much larger floods than what happened in 1862 from these sediment records. It is not the largest by far within the past millennium of deposits. So that is further evidence that we really need to be thinking about this, especially if the odds are going up. I would also emphasize that there, as far as we know, there's no actual cycle. There's no inherent periodicity. It's not like they occur for a particular physical reason every 200 years.
Mm-hmm.
The way that's actually calculated is you look at a millennium, so 1,000 consecutive years of deposits essentially, and in that 1,000-year record, you find about 5 events. They could happen 2 years apart from each other. They could be 500 years apart. It just means that over that period, it occurred about 5 times. So on average, it's about 200 years. But there's no physical reason for that to be cyclical. And this is often a misnomer when we talk about recurrence intervals, like the 100-year flood. Does not mean it happens, like clockwork every 100 years or even close to it. It just means that on average, there's a 1% chance that it happens in any given year. So the 200-year flood just means that there's a 0.5% chance on average that it happens in any given year. So hopefully that helps clarify the background, the return period language a bit.
Sorry, because we are going to need to wrap up here. I just wanted to note that I dropped a link in the chat to an in-depth article that Daniel was interviewed for, and several others were in Mother Jones on the biblical floods in California, that give you some of the how you're deriving some of this information and information on floods prior to the 1862 floods. Okay, this may be our last question that we have time for right now. How will a warmer climate impact monsoonal moisture and precipitation in Southern California? So I think they're thinking a little more inland.
Yeah, it's a good question. And it's interesting because even though only the only part of California that gets a meaningful amount of its annual precipitation from the summer monsoon are the far southeastern deserts, it does sort of have an outsized impact even areas elsewhere, not in terms of how much precipitation there is, but in terms of the frequency of lightning, because it's really the only mechanism to develop these sorts of dry lightning events like we saw last summer in the Northern California coast that can produce all these fires. So it is consequential for other reasons, even though it very rarely brings a meaningful amount of moisture. And the answer is essentially, we don't know yet, but again, I'll hazard a guess. There actually is a little bit of evidence that the western fringe of the monsoon may become a little bit more active. I don't know if that's good news though, because if you bring twice as much rain to San Francisco in July, it's still almost no rain. But it means that what you may end up seeing are a somewhat increased frequency of these lightning events that don't bring a lot of water. So that's a low confidence statement. I'm just sort of hazarding a guess, but that's actually something that another colleague of mine emailed me about this week that I think we're going to be pursuing over the next 6 months or so. So stay tuned, I guess.
Great. We only have a few more questions here, but we are kind of running out of time. There are some questions about recharging groundwater and about using reclaimed water systems that Daniel, happy to have you talk about that, or I can address that a little bit as well. So the question is, to recharge groundwater, wouldn't you have to increase the size of floodplains?
I'm not a hydrologist or aquifer expert, but the answer is not necessarily, and you could actually do that even if you needed to strategically. One of the things that I'm trying to really work with the Nature Conservancy right now is this notion of dynamic floodplains. In other words, it doesn't have to be a fixed thing. Natural floodplains are not fixed. And what you might be able to do is, especially in places like the Central Valley, where you have some lower population density areas that are used for agriculture primarily, you don't have to devote an area to be a floodplain 100% of the time. You can have field crops or even orchards, depending on the details, that you can afford to inundate for a couple weeks at a time, if and when necessary, and if and when the water is available. So most of the time, even in most years, that never happens. But say the 20-year, the 50-year recurrence interval flood comes along, you might say, hey, is it okay? Do we have a pre-existing agreement that we can flood your fields for a month when the really big flood comes, and we'll pay you for that, or you'll get some benefit to compensate for the fact that we're going to flood your field this year, but next year it'll be back to normal.
Yeah.
There are ways to actually actively expand the floodplains. Easier said than done, obviously, but it's not impossible.
Yeah, and I thinking about this, I do a lot of work on the Los Angeles River, which the lower Los Angeles River is primarily channelized, like so many rivers in Southern California. And a lot of what we're doing, both to think about increasing groundwater storage as well as habitat areas, are there parcels we can buy that are adjacent to the channel where we can cut through or develop, piping system to bring water off of the main flow and inundate some areas that will probably be used for habitat at other times of year, not so much for agriculture, but.
Yeah, that's an interesting, I think this is an interesting way of framing it, that it may, in some places you can't bring back the natural floodplain for practical reasons. I mean, in a concrete river channel with movie studios on one side and apartments on the other, as is the case with a lot of the LA River, there's only so much space to move. But if you can find ways of actively moving some of that water to where you do have the space relatively close by, that may be the way to do this, is to sort of create new floodplains in different kinds of places that aren't necessarily immediately river adjacent. That actually is an opportunity to achieve this.
Yeah, can we recreate the ecosystem services that those floodplains would have provided in the past, kind of thing. Okay, I think that we're now at 6:01. We should probably call it. I'm sure we could talk for hours more about all of these issues. Please, if you haven't already, follow Weather West, where you can get some more information about a lot of these issues. Consider participating in the Climate Stewards program, where you can really delve into understanding these issues and then also thinking about what you can do to help your community address them. And with that, I don't know if Annemiek, if you want to close us out, I'll just say on my part, see you tomorrow.
Yes, and thanks again, all of you. It was very, very enlightening. See you tomorrow. Bye.
Bye.
Bye.